We'll wait for 2 more minutes. Let if other join, or else we'll start at 6:10. Okay, so we'll start the session now. I have shared the screen. Okay, so hello all. So today we are going to discuss about the week 6 lectures, or some of the assignment questions, not the real one, but some of the assignment questions which will deal for the lecture 6 or week 6 lectures. I hope you guys have gone through the lecture 6 videos. Okay. So hello all, I'm Balram Shah. I'm the PMRF TA for this course, that is Watershed Hydrology, given by Agricultural and Food Engineering Department from IIT Kharagpur. So I'm a PhD scholar at Interdisciplinary Center for Water Research at Indian Institute of Science, Bangalore. So just I just stop the sharing here, and I'll switch off the video so the bandwidth is fine. Yeah. Yeah, so before moving on to the questions, assignment questions part, so what all we have learned till now, we have learned what is hydrology and watershed, then the hydrological components such as precipitation, evapotranspiration, then runoff, stream flow, and so on, and all other hydrological components. Then from that, we moved on to one of the important uh, part of the hydrology, that is hydrograph. And so in the last week we have discussed about what is hydrograph, what are direct runoff hydrograph, then what is ERH, then what is unit hydrograph. So with that we'll continue today, and we'll talk about and in these lectures we have seen that we are going through the synthetic unit hydrograph, and then we have also seen the instantaneous unit hydrograph. So we'll do some questions on that, and I'll just go through those concepts once. Okay, so before moving on, just let me go to So in this we have seen that we are talking about synthetic unit hydrograph, right? So the first question that arises is what is synthetic unit hydrograph and why we are going to use synthetic unit hydrograph. So we know, let's say, several basins, maybe small watersheds or small catchment, small watershed or small catchments can have uh, the things like they don't have meteorological data such as precipitation, temperature, or they don't have maybe hydrological data such as stream flow, runoff, etc. Right. So for those catchments, if you want to do some prediction, or let's say if we do want to do some hydrological analysis, so in that case we need, what we do, we use the unit hydrograph from our known source or wherever we have the data, right? So from there we create a unit hydrograph for that catchment and then we use that to do further analysis. So for this this concept, that is, or this topic, that is prediction in ungauged catchments, had been a great topic which has been dealt by the researchers and scientists for around decades, around maybe 10 years or more than that now, right? So mostly we use this synthetic hydrograph for ungauged catchments, right? Or which are small and which has less data or no data, like that. Okay. So for such watersheds, we use these unit hydrographs, and these unit hydrographs are derived from mostly empirical equations. Sorry. So mostly what we do, or what we have seen, is that researchers have used several data wherever we have, like maybe nearby neighboring catchments are there, or let's say some hydrological similar catchments are there. Based on the data that we have from there, what we do, we create empirical equations so that we can use that to do the predictions or any hydrological analysis in the catchments which we are intended to, right? So these empirical equations relates with the watershed characteristics, mostly watershed characteristics, and then we'll also see that how it deals with other characteristics of catchment such as shapes, size, then storage of the catchment, and so on. Okay, so therefore the unit hydrograph derived from such equations, we call that as synthetic unit hydrograph, right? So there are four popular methods we have seen in the lectures which we can use to develop the synthetic unit hydrograph for any ungauged catchment, and those are Snyder's method, then we have seen SCS dimensionless unit hydrograph method, right? Then we have also seen SCS triangular unit hydrograph method, and last but not the least we have also seen the time area method. So as it has, all these methods has been explained in very detail in the class or in the lecture, I'll not go into very detail, but I'll just touch upon these and I'll mainly focus on the questions or assignment questions, right? So starting with that, first method that was there was Snyder method, and this method is called Snyder method because it was given by Snyder. Okay, so he created, or he developed a parametric unit hydrograph and called it as standard unit hydrograph. Okay, so what he did, he has related the characteristics of this unit hydrograph to the watershed characteristics, right? So the standard unit hydrograph is characterized by relation between. So we have studied the unit hydrograph last time, right? So in that we have several. So it starts from zero, right? But here we'll have some basin lag for the synthetic body, right? So it was discharge. Let's say in Qmax, and here we had time. Let's say in hours. Okay. So we have also seen here the effective rainfall that we had, and we called this as the duration, right? So let's say we call this as effective rainfall duration, that is TR. Okay. And then we have basin lag. What is basin lag? Basin lag is generally defined as the, in synthetic unit hydrograph, it is defined as the time lag between the center of mass of the wait, center of mass of the effective rainfall to the center of mass of the unit hydrograph. We call this as basin lag, right? So in the last class also for unit hydrograph, what we have seen that we call the basin lag as the time lag between the center of mass from of the effective rainfall to the center of mass of the unit hydrograph. For in this case, it will be generally so I'll write that. So basin lag, we call that as TP, is the time lag to peak. Generally, we have this is hours. So what does this mean? That the time from the center of mass of the effective rainfall to the peak of the unit hydrograph here. So here we have the peak, and we call this as the peak direct runoff rate. Okay, so here QP is what? QP is the peak direct runoff rate per unit area of the basin. And as it is per unit area of the basin, the unit will be in cubic per kilometer square, right? Other than that, we had base time also, right? So base time, in that case, it starts from zero, because here what we have here, it starts from the some lag from the effective rainfall. So here we call whenever it is starting. So here the time base is what? The time base is the where we are our hydrograph starts and to the end of the. So this we call as time base, right? Okay. So to create synthetic unit hydrograph from Snyder's method, we have also seen we have like for smooth curve, we get the value for this, that is W75 and also W50. Let's say this is the W50. These are the widths W50. So these are the width of the hydrograph at 50% of peak, and this is at 75% of peak, and both of these are in hours. Okay. So and this basin lag, whatever we have studied, this what is the physical meaning for this basin lag? The physical meaning for this basin lag is like it is the time delay between the occurrence of rainfall and the corresponding peak of the resulting hydrograph at the watershed's outlet, right? So according to Snyder's method, basin lag, we write that as TP is equals to 0.75 into CT into L into LCA to the power 0.3, right? So here you see there are two constants. One is 0.75, then we have CT. CT is also a constant which varies from zero point 0.3 to zero point 0.6. So other than the watershed characteristics like L and LCA, what is L and LCA? L is the length of the mainstream from the outlet to the divide. So let's say this is the we have the catchment. Okay, right, and this is the outlet, let's say. So the total length from the outlet to the remotest point, we call that as, or let's say this is the one, so let's say this one, so this we call as L, and let's say the centroid is here. Okay, so the uh, so the so the nearest point from the centroid to the stream, if we take a length from there to here, we call that as LCA or LCA. It's taking small, right? So LCA is what? LCA is the distance from the outlet to a point on the stream nearest to the centroid of the watershed, and both of this we take is and in kilometers. Okay. So here this constants, that is CT 0.75, it takes into account the other characteristics of the watershed. So here for instance, CT depends on the type and location of the stream. So let's say if we have a steeper slope, this means what? This means the CT value will be more. So this means what? That CT is depends on kind of geomorphological characteristics of the watershed, right? And this the quantity, that is L into LCA. This is a measure of the size and shape of the watershed. So no, it does not only depend on the watershed characteristic, the synthetic unit hydrograph, but also on the shape and size of the watershed, then how steep it is or the slope, something like that, right? So yeah, so we have seen how we can get the basin lag, right? So similarly, we can get the peak runoff rate, that is QP. We write it as 2.78 into CP divided by TP. So TP we got from the last equation, right? This, and then here again this CP is also constant, right? And it ranges from 0.56 to 0.69. Okay. So this CP represents the storage coefficient, which depends on the storage of the watershed or how much it can retain. This means retention of the storage watershed and so on. Okay, so both these constants, that is CP and CT, uh, so we use this for a standard unit hydrograph, and we can develop this. So for, let's say, for one watershed, uh, let's say watershed A. So for that, if some other hydrological similar watershed we have, let's say watershed B, and we know the CT and CP value of watershed A, then we can use that CT and CP value to get the characteristics or to get the synthetic unit hydrograph or of the hydrological similar watershed, let's say watershed B. So we'll use the same value and then we can get the other information, right? Okay. So like that we can get the base time, which we write as 5.56 by QB. Then we get W50, that is 2.14 by QP to the power 1.08, and then W75, that is equals to 1.22 by QP to the power 1.08. If you just notice here, the denominator is same, that is QP to the power 1.08. So W50 is where, see, the width should be more, and hence the numerator value is more. And here in W75 1.22, it is less because the width should be less, right? And to note that, let's say if the synthetic unit hydrograph is needed for duration capital TR, so which is different from this small tr. So TR is what? Here TR is the uh, duration for the effective rainfall. So if the duration that we need for synthetic unit hydrograph is different from this TR, then what we do? Then the standard basin lag, we modify that with the equation, that is TP dash is equals to TP plus TR minus TR, where this TR is the small TR. This is the effective rainfall duration, and capital TR is the duration for which we need the synthetic unit hydrograph divided by 4. Okay. Okay, so why we use this Snyder's method? Because there are few advantages. That is, in this you see that it is very simple and straightforward. Just use these equations and then you can reach to the synthetic unit hydrograph, right? And it does not require any high complex calculation or extensive data inputs, right? Also, we can use this Snyder method to watershed with limited or no stream flow data. So let's say if limited data is there or no stream flow data is there, still we can use this Snyder's method. So these are the advantages. There are few limitations also. So like as I mentioned in the beginning only, that these whatever synthetic unit hydrograph methods we are going to see, these are applicable for small watershed. So this method is suitable for a small or medium sized watershed, and hence we can't use this for a large or more complex watersheds. Okay, this is one of the limitations. Second limitation is that let's say if non-uniform rainfall distribution is there for the watershed, then what we do, we can't use this Snyder's method very easily, because it what is the assumptions whenever I have several explained a method, or that time I mentioned that we should understand or we should know the assumptions that are behind that method, because that assumptions will only tell you that when to use this method and when not to. And we have seen that this Snyder's method assumes that a single effective rainfall hydrograph for the entire watershed, and hence for the assumption is that it should have uniform rainfall duration. So for non-uniform rainfall duration we can't use that, right? Okay, so with this we'll just do some questions. Yeah. So the first question is, Snyder defined a standard unit hydrograph as one whose rainfall duration TR is related to basin lag TP by. So we have just seen this, right? We have seen that for Snyder's method, how do we write TR? TR was the effective rainfall duration. This is what? This is the duration of, sorry, duration of effective rainfall, right? TR is equals to TP by 5.5, where TP is what? TP is the basin lag, right? So from this we can see that we can write this as TP equals to 5.5 into TR, right? So the correct answer will be A, right? Okay, so we'll move to the next question now. So in hydrology, the step response function is commonly called as, so we have seen this in the last class also. So the correct answer will be S hydrograph, right? We will see this in today's IUH, that is Instantaneous unit hydrograph also. So the correct answer will be B. Okay, so next question is, different synthetic unit hydrographs are derived based on. Okay, I'll give you 1 minute for this. Just think, and then I'll give answer, and then you can just check if your answers that you thought is correct or not. Okay, any guesses? Okay, see. So here it is mentioning that different synthetic unit hydrographs, right, are derived based on. So we have just seen it is Snyder's one is based on watershed characteristics. Then it is also based on hydrograph characteristic and geomorphological characteristics. And before that, I have mentioned that there are four popular methods. Other than that, also we have several methods, right? So one of them is the SCS dimensionless hydrograph method, right? So a dimensionless unit hydrograph is also used, and then models of catchment storage as storage coefficient is there, right? That CP, as we mentioned, that CP, what it denotes? It denotes the retention or the storage of the watershed, right? So all these four uh, will be used for different synthetic unit hydrographs. Okay, so the correct answer will be all the four. Okay. I hope it is clear. Okay, so we'll move to the next question now. The next question is the peak discharge per unit area of a drainage basin is 0.5 cubic per kilometer square. According to Snyder's method, the width of the hydrograph at 50% of the peak discharge, right? So what we have, okay, I'll give 1 minute. You guys can just try once. Okay. Okay, so any updates on this? Did you try? I'll I suggest you guys to like do along with when we are having this tutorial session because it will help you. If you have doubt, you can ask directly this time, right? So this is mostly for the doubt clearing session and all, right? Okay. Okay, nothing. Okay, so we'll start then. So what is given? The peak discharge per unit area is given for a drainage basin. So we have seen that QP that we have denoted is the peak discharge per unit area of the basin. That is, here it is 0.45 cubic per kilometer square. So according to, we need the width of the hydrograph at 50% of the peak discharge. So we need W 50, right? So formula we have seen. What was the formula again? So W50 equals to 2.14 QP to the power 1.08, right? W50 is equals to 2.14 QP to the power 1.08. That is equals to 2.14 divided by 0.45 to the power 1.08. Just do it once. Let me see how much we are getting. So I'm getting something like 5.069 hours, right? Yeah, so it is something near to 5.07 hours. So the correct answer is C, right? Any questions on this? Okay, if not, we'll move to the next question then. Yeah. So the widths of synthetic unit hydrograph are distributed with respect to peak as. So we have seen the mostly the widths of the synthetic unit hydrograph we see. One third of the widths are distributed before the peak, and then two thirds of the widths are distributed after the peak. So we have seen while doing the unit hydrograph also similar thing happens to synthetic and unit hydrograph. Mostly it will be skewed. So one third of the widths are distributed before the peak, and two thirds of the widths not before the peak but after the peak, right? So correct answer will be both A and D. Okay. Okay. Any questions on this? Okay, if not, if I can move to the next question now. Okay, so before this, we'll just see the SES dimensionless unit hydrograph first. Okay, so we have seen that second method that we have seen was SCS dimensionless hydrograph method, right? Okay, and as the method's name only suggests that it is given by or it was employed by SCS, that is Soil Conservation Service. So what they did was, so they took several catchments with different size and having different geographic locations, and based on that they created so many unit hydrographs or natural unit hydrographs. So based on the number of watersheds they have taken, based on the size and based on the geographical locations, they have created a large number of unit hydrographs, and from that they have derived an average dimensionless hydrograph. So an average dimensionless hydrograph, and this was used for as the SES dimensionless hydrograph, right? So in this, as you can see, that it is dimensionless hydrograph. So the dimension for the x-axis and y-axis that we have seen in the last class, it was discharge versus time, right? So here what we are doing, we are making those as dimensionless. Hence we are using discharge ratio in the y-axis, which is given as, sorry, q by qp, right? And in the x-axis we use time ratio, that is t by tp. Okay. So here QP, we know that this is the peak discharge and Q is the discharge at any point, right? And TP again is the time at the peak. Okay, time to peak. Okay, so something like this will come. So mostly this time to peak is located at 20% of the time base. Okay, and the inflection point we have seen, remember that we have seen A, B, C, D, E, where it starts, and then we have inflection points. Here we have peak, and then the recession limb. So these inflection point, the next inflection point that you see is located at 1.7 times that of the time to peak. Inflection point is located at 1.7 of TP. Okay. So this discharge ratio versus time ratio, SCS has given one table. So in that table, for time ratio, it starts from the time ratio starts from. So let's say if I write time ratio, in that table it starts from 0 and it varies till 5 hours. But no, it's dimensionless, so we don't have any unit for that. And for each of this time ratio, we have discharge ratio values also, and for that we also have mass curve ratios also. Okay. Okay, so with this I'll just do some questions. So we're here. Okay, so the question is, time base of the synthetic dimensionless SCS unit hydrograph is. Just tell me what will be the answer, everyone. The correct answer will be A, that is 2.67, right? So this is generally that is used is 2.67. Okay. Okay, so the next question is, for a basin area of 3 kilometers square, the area is given for the basin. The time of concentration is 1.25 hours. Anyway, the time of concentration we have dealt so many times. What is that? 4 hour for a 1 hour triangular synthetic hydrograph. So the triangular okay. So we have triangular synthetic hydrograph. The time to peak or time of rising is. Okay. So before that, we'll just see what is this SCS triangular hydrograph, right? Okay, so the triangular unit hydrograph. So in this, if you see what the CS has given is, we can consider this hydrograph which we have seen. It will be a smooth curve, like something like this, right? So according to SCS, we can consider this something as a triangle. Okay, something like this, and this peak, generally the left to this will be 3/8 part, and the right will be 5/8 part. Okay, so again, as it is given, it will be the time ratio, and in the y axis it will be the discharge ratio, right? Okay, and this will be the duration, let's say. So let's say the duration be d. Okay, so from the centroid, the time lag is given as TL. Okay, so this one is the time to peak. I'm not going again into that, and the total time is the time of base time. We know all those things. So empirical equation given was the for the triangular unit hydrograph is the time base is given as just in this. Sorry. Time base TB is given as 2.67 into TP that we have just seen in the questions before, right? So this is how we can get the time base of the unit hydrograph, right? Now if you see the recession limb, so recession limb we know where the hydrograph starts decreasing, right? So in that the TR is given as, so we know, see this is the total time is base time. So if you want to know this, that is the recession time TR, how will you find that? TR will be equals to TB minus TP. So just from this also you can understand that how to find that. Okay. So the time to peak or peak discharge is given as, sorry, the peak discharge is given as 0.75 into Q divided by TP. Okay. So this capital Q is what? Capital Q is the volume of direct runoff. And this capital Q also we have the empirical equation. We write Q as QP by 2 into TP plus TR. So all these terms you know now. So how do we find this QP? QP we find as 0.75 by TP. Okay, because see the volume of the direct runoff under the unit hydrograph is always 1 centimeter, right? Hence the peak discharge can be calculated as this, that is 0.75 by TP. Okay, and let's say if you so this one will be in centimeter per hour. Now let's say if you want this peak discharge in volumetric unit, right, in Qmex, so you can write that as 2.78 into A divided by TP, where this QP will be in Qmex. So A is, we know A is the area, drainage area. We'll write this as drainage area, which is in square kilometer, right? And yeah, so TL was also left. So this TL is equals to 0.6 into TC. So we'll not go into that much in deep, but TC is the time of concentration. The time of concentration. Okay. So here also if you see, so if you see this uh, time to peak is what? Here, right? TP. So if you see TP, how you can write TP if your D and TL is given? From the figure also you can say. Can you tell me how? If I want to know what is TP, how can I write TP? How can I write TP? Then can you tell me from the figure? You have given D and TL is given. Okay, so how we can write? See, from the figure you can say that D by 2 plus TL, right? And TL also you have 0.6 into TC. So from there, if you like, let's say if you have the time of concentration and you have the duration of the effective rainfall, then from there you can find out TL also. TL will be equals to D by 2 plus 0.6 into TC, correct? Okay. And generally this duration D, if it is not given, it is generally 0.133 into TC, where TC is the time of concentration. Okay. So with this, we'll move to the question again. So all this formula is there in the lecture also, you can just see there. Okay, so see this question. I'll give 2 minutes for this. Let me know how much you are getting. Okay, anyone? Anything you guys got? Okay, if not, I'll just do it. So what all is given? We have the area as 3 kilometers square. Then we have the time of concentration TC as 1.25 hours, right? And then we have the effective rainfall duration, that is 1 hour, right? Now what we have to find? We have to find the time to peak or the time of rising. So we know time to peak equals to, we have just seen, right? Time to peak equals duration by 2, that is TR here. Okay, so we should not write TR because it was in our figure, it was, we have written it as D. I will write it as D only. D. So D by 2 plus zero point 0.6 into TC, correct? We have just seen this. So just D is equals to 1 by 2 plus 0.6 into TC, how much? 1.25. Just calculate this, how much we are getting. 0.6 into 1.25 plus 0.5. I'm getting something like 1.25 hours. So the correct answer will be B, that is 1.25 hours. Any questions on this? Okay, so we'll move to the next question now. So the next question is, a catchment is having an area of 3 kilometers square for which the time of concentration is 1.25 hours again. Okay, so the data is same. We just need to find out the peak discharge, right? So from the earlier one, so we'll write it again. Is 3 kilometers square. Then time of concentration is 1.25 hours and duration is 1 hour. Sorry, 1 hour. And then we also got time to peak as much, 1.25 hours, correct? And we need to find out the peak discharge. So we have just seen the formula for peak discharge. What was that? See, peak discharge formula was what? It was, okay, so that one will be there in the figure also. Yeah, so it is something like 2.78 A by TP. So just use that. So we have peak discharge QP equals 2.78 into A by TP. So TP we have from the last question. So we can just put it here, 2.78 into 3 by 1.25. How much we are getting? 2.78 into 3 divided by 1.25. Okay, so we are getting something like 6.67 meter cube per second. Okay. Yeah. Okay, so the range is given from 4.9 to 5. Okay. Somewhere in maybe this constant varies for watershed to watershed. So because of that, in this question it might be varying. Somewhere it is also given as, in some books you will see it is given as 2.08 into A by TP. So if you just go like that, then 2.08 into 3 divided by 1.25, that is how much we are getting? 2.08 into 3 by 1.25, something like 4.992 meter cube per second. Okay, so we can get in this range. So for now, we'll just use this. Okay, okay. So we'll move to the next question. Uh, Here, any question? So in this problem, any question? Okay, if not, we'll move to the next question then. Okay, so the next question is, what is that? Okay. So a catchment is having an area of 3 kilometers square again. So again, the same data, just we need to find out the time base. Okay. So what all we have now? We have A equals to 3 kilometers square. We have time of concentration as 1.25 hours. We have duration is 1 hour. We have time to peak as 1.25 hours again. And we have QP as, let's say, 4.992 meter cube per second. Okay. So we just need to find out the time base, right? Time base, we know time base was given as 2.67 into TP, right? Okay, so for now, we'll just keep, sorry, yeah, so we'll just keep the above one on this one, 6.67. And make this a 7 maybe. Okay, so based on some books, they also give this. So mostly it was given by SCS, so it was like that. Okay, so we were on the base 10, right? So just put the values, that is 2.67 into TP was how much? 1.25. Just multiply that and you get the answer. Can you tell me how much you're getting? I'm getting something like 3.34 hours. Yeah, so the range is between that. Okay, any questions here? Okay, if not, we'll move to the next question then. Right. So the next question is, watershed A having the 2-hour unit hydrograph from the observed rainfall and runoff of an isolated storm on it has the following characteristics. So watershed A has the following characteristics, that is basin lag TP, sorry, TP, right? Basin lag we denoted with TL, I guess, right? Let's see, basin lag was given by what? From basin lag we did TP only. Okay, so basin lag TP is equals to 24 hours. Then peak discharge QP is equals to 50 meter cube per second. Then area is equals to 700 kilometers square. L is given as 30 kilometer, and LC or LCA, let's say, is given as 50 kilometer. Okay, and again we have watershed P. which was hydrological similar to watershed A, has the following characteristics. That is, area is given as 1200 kilometers square, L was given as 120 kilometer, and LC or LCA is given as 100 kilometer. So the here you see watershed A having the 2-hour unit hydrograph is there. Okay, and we need what, the peak of the 4-hour synthetic unit hydrograph for watershed B using Snyder's method. We have to do. We'll give you 2-3 minutes at least start. Then I'll also do. Uh, so okay, I'll also do. Let me just take one more slide for this. Okay, so first we'll check. First we'll check whether the derived unit hydrograph of watershed A is standard unit hydrograph or not, right? So that is the first step we need to do. So how we check that? We just see if the time to peak is matching the or the effective rainfall time is matching the uh, given or the one which we are going to find out, right? So we know TP is equals to 5.5 into TR, right? So from this you can find out the TR, sorry, TP you can find out here, right? So 5.5 effective rainfall duration was how much in watershed A? It was 2 hours, right? We will just multiply that 5.5 into 2. How much we are getting? Just 11 hours, right? Right? Is that the one we have, which we have? Whether the effective rainfall duration that we have is matching this? No, right? So what was the formula for that? So here you can see that TP, that is we have the TP is 11 hours, right? So the formula that we have to use will be TP dash, right? Just check the formula once. So we'll use TP dash equals 21 by, sorry, 21 by 22 TP plus TR by 4, right? How much it will be? Can you just tell me? Basin lag was how much? Basin lag was 24 hours, right? We have here how much? 11 hours. So 11 hours is obviously not equals to 24 hours. So that's why we are using this, right? So TP dash will be equals to 21 by 22. TP is how much? 24 plus TR is how much? 2 by 4. Just calculate and let me know how much you are getting. Yes. 5 plus that formula. You guys also do, I'll just calculate this. TP is how much? 24. 4 plus capital TR. Okay, or else we can directly use because we are just doing that. Sorry. Okay, so we have, if you just see that, how much you are getting. Because we need to find out the TP dash. So TP dash, sorry. TP dash equals 22 by 21 here into how much we have? 24 hours TP, right? Okay. So here TP equals to 24 hours, right? So 24 minus 2 by 4. Just if you see the figure, you can do this. So how much you are getting? 4 minus 0.5, that is 23.5. 22 by 21, how much you are getting? 22 into 23.5 divided by 21. Something like 24.619 hours. Correct? Now, so with this we can, now we have need to find out the coefficient, that is CT and CP, because we have given that this watershed B is hydrologically similar to that of watershed A. So the coefficient I mentioned while discussing that if it is hydrological similar, then the coefficient, that is CT and CP of watershed A, we can use that for watershed B also. So the firstly we have to find out the CT and CP from watershed A. We will use that in watershed B to calculate whatever we need here, right? So we can write CT as CT equals What was the one more thing? 1 minute. Sorry. Yeah, here. Yeah, so CT equals to TP by 0.75 into LCA to the power 0.3. Just add this slide. Okay, so CT equals to TP by, so here always we'll use the TP dash now, right? So TP divided by, like TP dash divided by 0.75 into L into LCA or LC to the power 0.3, right? So TP we have 24.619 divided by 0.75 into L is how much? L was given as 30 kilometer. 30 into 15 to the power 0.3. Just calculate and let me know how much you are getting. Divided by 0.75 divided by 30 into 15 to the power 3. 3 into 0.75. So that means what? I'm getting into the range. Just check. 0.3 to 0.6. Okay, but here it's not in the range because the watershed is different anyway. I'm getting something like 5.251. Okay, and CP, how much we are getting? We calculate CP. CP equals, how much it was? QP. The formula for CP again. Yeah, 2.78 CP. Okay, so TP into QP by 2.78. Into TP by 2.78, right? So QP can be written as how much it was, 50 meter cube per second. So 50 into 24.619 divided by 2.78. How much we are getting? Also, this QP was per unit area it should be, so we'll divide with the area, that is 700 kilometers square. Okay, so how much we are getting? 50 into 24.619 divided by 2.78 into 700. Something like 0.632. Okay, so now we have the CP and CT for watershed A. Now we need the required unit hydrograph for watershed B, right? So for watershed B, we can write basin lag TP is equals to 0.75 into CT into L into LC to the power 0.3, right? We have 0.75 into 5 point, how much it was, 5.251 into L is how much? L for watershed P was 120 and LC is 100. So 120 into 100 to the power 0.3. Okay, just calculate and let me know how much you are getting. So what happened? Give me a minute. I hope you can see the screen again. Okay. Like 65.9 hours. Okay, and TR will be equals to how much we have? TP by 5.5, that is 65.9 divided by 5.5, it is 11.982 hours, right? So again you see TR is how much? 24 is not again equal to this, so we have to find out TP dash again. So TP dash is equals to TP minus TR minus TR divided by 4, right? That is equals to 65.9 minus 11.982. Plus so how much we have to find? Peak was how much? We got the 4 hours in the table. 4 divided by 4. How much we are getting? 11.982 minus 4. 4. 5.9 minus 1. Somewhere near 63.9 hours. Right? Therefore, time to peak will be TB dash plus TR1, not TR, T by 2. That is equals to 63.9 plus 4 by 2. That is equals to 1, 2, 3, that is 65.9 hours. Okay. So QP equals to 2.78 into CP, because we need what? See, we need the peak of the 4-hour unit hydrograph. So QP equals to 2.78 into CP by TB dash. That is equals to 2.78. CP how much we got? 0.632 divided by TP how much we got? 65.9. That is equals to somewhere near 2.78 into 0.632 divided by 65.9. 0.03 somewhere. 0.03 meter cube per second per kilometer square, right? Because it is QP, so that is cubic per kilometer square. Therefore, the peak will be QP is equals to 0.03 into the area. Area was how much? 1200 kilometer square. So 0.03 into 1200. 36 meter cube per second. 36 meter cube per second. Okay. The range here is 68 to 70. There is some either calculation mistake. So the question I have taken, I think the answer there was not correct. So answer will be how much? 36 meter cube per second. Okay. write it here, 36 meter cube per second. Okay, so any question here in this? If not, we'll move to the next question then. Okay, no questions? Okay, so we'll move to the next question. Okay, so next question again, the data is same, that is watershed A having the 2 hour unit hydrograph. Same watershed A has the basin lag, peak discharge, area, L and LC. Similarly, the watershed B again is hydrologically similar. The question is same, thus just the thing is we need to find the time of rising or time to peak. Okay. So time to peak we got in the last one, right? How much it was? Time to peak was, this one is the time to peak. So the correct answer will be 65.9 hours. Okay, so again, I think the calculation was wrong for the variable we have taken. So the correct answer will be how much? 65.9 hours. It will be 65.9 hours. Okay. It might be possible that I have done some calculation mistake. Just check once. Okay. Okay. Any questions here? So I have just directly taken from the last question, last solution that we have just done. Okay. Okay. Any questions? Okay. If not, we'll move to the next question again. So the next question again it is same. Just we need to find out the time base for the required synthetic unit hydrograph. So we know time base, how we can find time base TB equals to QP by, sorry, 5.5 by QP, right? 5.56 by QP, that is equals to 5.56 divided by QP is how much? 0.03, right? Yeah, 0.03. So 5.56 divided by, sorry, 0.03, somewhere near 185.3 hours. Again here I will mistake. It will be 185.3 hours. Okay. Any question? This is simple. We'll use the equation. We'll get to the solution. That's it. Okay. Okay. So the next question is, an instantaneous unit hydrograph is a hydrograph. So we have also studied what is instantaneous unit hydrograph, right? What is instantaneous unit hydrograph? Anyone? Mm, no? Okay. So we'll move to the slide then. So next was the instantaneous unit hydrograph, or we write this as IUH. Okay. So what is instantaneous unit hydrograph? Again, from the word you can understand that instantaneous unit hydrograph is like uh, the response of a watershed to a unit input of rainfall over a short duration. Because see, it's instantaneous. This means it is having short duration, or you can say it as, or the D that we have discussed is diminished indefinitely. right? So the duration will be like very very small, very infinitely small, but as the volume of the unit hydrograph should always be 1, right, 1 centimeter, because it should be unit hydrograph. So this means that it should be unit input of rainfall, correct? So the unit hydrograph that we'll obtain from this, we'll call that as instantaneous unit hydrograph. So if you write this instantaneous unit hydrograph, the you will get a direct delta function, right? Or just a response function, we say. So it will be like h at any short duration time will be equals to h of t, right? Where duration tends to 0 as a limit. So if you write limit b tends to 0, but volume remains 1 unit, correct? So we also write it as, let's say, ht is equals to h of 0 comma t, or limit t tends to 0 h of t comma t. Okay. So we have seen all this thing in lecture, that if unit input is applied like instantaneously at time, any time t, let's say, the response of that system at data time tau is given by unit impulse response function. Okay, I'm not going into those. We have just seen convolution theorem and all. Okay, so okay, with that we'll move to the questions now again, right? Yeah. So the question is, an instantaneous unit hydrograph is a hydrograph of, we have just seen that it should be infinitely small duration but unit amount of rainfall. So the correct answer will be B, that is infinitely small duration and unit rainfall excess, correct? Okay, so the next question is, a 90 km square catchment has a 4-hour unit hydrograph, which can be approximated as a triangle. So we have a triangular unit hydrograph, correct? And then if the peak ordinate of the unit hydrograph is 10 meter cube per second, the time base is how much? So, so if you just write the area under the unit hydrograph will be half into time base, let's say TB into uh, the peak ordinate is how much, 10 meter cube per second. So this should be equals to, because it's a unit hydrograph, right? So the rainfall will be 1 centimeter, or if you just change that to meter, 1 by 100 into how much is the area? Area is 90 kilometers square, right? So we'll write 90 into 10 to the power 6, because we are converting this kilometer square to meter square. Okay. So if you just calculate the time base, it will be 90 into 10 to the power 6 into 2 divided by 10 into 100. So 10 to the power 4 into 10 to the power 4. So this we are getting in seconds, right? So just change this to hours, because our options are in hours. 10 divided by 4 divided by 60 second per minute, hours. We'll get something like, let's calculate this. So the entire something like 50 hours we'll get. So the correct answer would be C. Any questions in this? Okay, if not, we'll move to the next question then. Okay, so the next question is, the time of concentration of a catchment area is 26 hours. The time to peak in hours of a 4-hour triangular shaped unit hydrograph, again we have triangular shaped unit hydrograph, and the time of concentration of a catchment area is given as 26 hours, right? And the duration is given as 4 hours. And we need time to peak. So we have the formula, that is Tp is equals to d by 2 plus 0.6 into Tc. Well, this we know is the time lag, right? That is TL. So that is 20, sorry, Oh, sorry. So D is 4 by 2 plus 0.6 into DC was how much? 26, right? So it will be तो 15.6 17.6 hours, right? So the correct answer will be B. Any questions in this? Correct answer will be B, right? Okay. The next question is the time media method for deriving a synthetic unit hydrograph is based on the principle of. So we have also seen the time. I think question didn't come. So the time media method for deriving a synthetic unit hydrograph, we have seen that among the four popular method, one is the time media method. In this, what we do, we see. So we basically take the isochrones. What is the isochrones? Isochrones are the line which joins equal amount of time of concentration, right? So or time of flow, let's say. So that is the time, and the area that is represented for that time of concentration, we call that as area for that isochrone, right? So the principle of isochrone is used. Okay, so the correct answer will be B. Okay, so the next question is the graph between the percentage of runoff occurring in successive periods of equal time interval of dr and the time interval is known as. So we have seen this in lectures. The correct answer will be distribution graph, right? Okay. So the next question is the x-axis of the dimensionless unit hydrograph usually consists of. We have seen that SES dimensionless unit hydrograph. The x-axis is time ratio, right, and the y-axis is discharge ratio. So this is the y-axis, and this is the x-axis, right? So the correct answer will be B. Okay. Next question we have. So the next question we have is in a triangular unit hydrograph, the time to peak flow is typically located at. So we have just seen that it will be 1/3 of the total duration from starting, right? So the correct answer will be 1/3 of the total duration. Okay. Any questions? Okay, we'll move to the next question then. So the next question is if the duration of a rainfall event is 2 hours, then according to the SCS triangular unit hydrograph, the time of concentration of the basin. So we know time of concentration of the basin is given as D by 0.133, right? That is 2 by 0.133. Just calculate how much you're getting. Something like 15.037. Okay, so that is 15.04 hours. So correct answer will be D. So just put the equation and then you will get the answer, right? Okay, so the next question is, I think this one is the last question now. If I tau, H and D tau are the intensity of rainfall, so I tau is the intensity of the rainfall, H is the ordinate of the hydrograph, and D tau is the infinitesimally small time respectively. Then the resulting direct runoff from the instantaneous unit hydrograph will be, so simple, that is I tau into H T minus tau, because just one lag we keep, right? The correct answer is D. Yeah. So with this, I will stop here. Do you guys have any questions, any doubts? If not, we'll stop here then. Okay, so we'll meet again in the next week, the same time, Monday 6 o'clock. Okay. Okay, so we'll stop the session here. Thank you.